Great pleasure to
So he
have.
told me to bend everybody off until he's here. Actually,
Get it.
So not to start until he comes.
yes.
No. Yeah. Okay. So today's first talk is by Tobias Koch, Rényi's Information Dimension Beyond I.I.D. Please go ahead.
Thank you. So, yeah, I have to turn on this. I'll do it very slowly so you also have a chance. So let's see. Great. So, okay, first of all, I would like to thank the organizers for inviting me, at least the ones who are here. I did a postdoc here in Cambridge like in 2010, so it's actually always nice to come back, especially if the weather's like that, which is obviously always like that in Cambridge, right? So what I'm going to present is joint work with my colleague Bernhard Geiger, who actually proposed to work on this problem, who was at the Technical University in Graz, and who's now in some research center in Austria as well. Okay, and well, so Rényi's work on information dimension is pretty much like a quest on understanding of what is the information content of general random variables. Okay, so I thought it's fitting to start with this like little story involving the two gentlemen on this slide. Right, you have like Wiener on one side, and you have Robert Fano on the other side. I don't know how much impact Robert Fano had on quantum information theory. I think classical is a very important figure. And I heard the reason why Robert Fano worked in information theory was the following. So Norbert Wiener, I think he was a bit of a particular guy, so he was walking around at MIT and he was shouting into the offices, information is entropy. And he liked these kind of things, and Robert Fano thought like, this is actually very intriguing, even though I have no clue what it means. So he started working in information theory to better understand what this is about. Okay. Anyway, so if you parse like this statement, information is entropy, obviously there are two words, information and entropy. And I think at least to like us working in classical information theory, I guess in the quantum case it's similar, it's always been clear that the information a random variable contains is actually equal to this uncertainty we have about x, right? So I make here this example about like where x is tomorrow's weather, right? It might be sunny or it might be raining. And then obviously the information x gives you is like equal to what you learn if somebody reveals x to you. And now, of course, not only depends on x itself, but it also depends on how much you know in advance. But if somebody tells me, well, in July it will be sunny tomorrow in Madrid, I won't be very impressed because the sun shines all the time. Whereas maybe if you're here in December in Cambridge, then it's a bit more interesting, right? So yeah, so information a random variable has is equal to the uncertainty. You didn't miss much. Good. Okay, so that's the information part. The entropy part is a bit more easy, right, because we have a formula for that. So suppose, for example, x is a discrete random variable with a given probability mass function. Then, well, this is how we define entropy. So this is, I think some of you guys call this Shannon entropy or von Neumann entropy. So for me, this is just entropy, and this is the only entropy I talk about in this talk. Right, and then I guess what we have to do, so if you want to know what is information, like, so if you want to understand this statement, information is entropy, we have to link the two things, so we have to somehow, or I have to convince you that entropy is a measure of uncertainty, right? It's, at least that's what we teach all the time in our classes, but in case you're a very skeptical person, so let me try. So, and well, I apologize in advance for dropping the I word once in a while, but so suppose we have a sequence of I.I.D. random variables, okay? So then we know by the asymptotic equipartition property that if we look at this like n samples, right, I.I.D. samples, then if n is large, then with very high probability, or well, almost all realizations actually of this sequence will have a probability that is equal to 2 to the minus n times the entropy. And they're roughly like 2 to the n times the entropy such realizations, so they're all these are equally likely, so you basically need n times the entropy bits to describe all those sequences, which basically means that the average uncertainty random variable x has is the entropy. This is, I think, one way of seeing that. There are other ways via compression and so on and so forth. Good. Now, so far what we did was for discrete random variables. Now suppose you want to know what is the information of a continuous random variable. So suppose x has a PDF. Now I studied electrical engineering, so I got a lot of, let's say, rule of thumbs that you probably can summarize as mathematics for dummies. So one of those rules I learned was, well, if you go from discrete to continuous, you just replace sums by the integrals and you replace the probability mass functions by the PDF, and then you will be fine, right? And if you're not fine, then it's not a practical example, right? It's usually, no, this is like a pathological mathematical thing that's not important to us, right? Now, if you do that, you get here what we call a differential entropy. Right? This is, and you can evaluate it for certain PDFs. But of course, the question is, does this really measure the entropy of a random variable? And it's always good to go back to Shannon's work and sort of see like what he thought about that. And Shannon's take on like continuous random variables is the following. So basically he said, and this is from his like original paper on a mathematical theory of communications, so where he says, to a considerable extent, the continuous case can be obtained through a limiting process from the discrete case by dividing the continuum of messages and signals into a large but finite number of small regions. And then you calculate the parameters involved on a discrete basis. And then as the size of the regions is decreased, these parameters in general approach as limits the proper values for the continuous case. Now just let's show a picture for that. So suppose you have a real valued random variable, then what you can do is you can divide the real line into intervals. You assign to each of those intervals a probability by integrating the PDF over that. And then you can compute the entropy for these. And then you let the sort of regions become smaller, and then the question is, to what does this entropy converge to, right? And well, if we believe like the mathematics for dummies approach, then we would somehow hope that this converges to differential entropy. But so the question is, does it converge to differential entropy? And if it doesn't, to what does it converge to, right? Actually, this approach also works if your random variable doesn't have a PDF. So it's actually a very nice idea. So if your random variable has some general distribution that can have discrete parts and continuous parts and singular parts, then still this approach actually works. You can still always do it. This is a well-defined approach. And this is pretty much behind the idea of what Rényi information dimension is. So a little bit of notation here. So this square bracket with the m here, I use that to denote like a quantization of the random variable x by using a uniform quantizer. So you basically have a uniform quantizer of step size 1 over m, and this is the quantized version. And what Rényi did is he computed the entropy of this quantized version, then he divided by log m, and then he let m tend to infinity. Okay? Now the limit does not necessarily always exist, but if it doesn't exist, you can just replace limit by lim sup or lim inf, so you can always come up with something that is defined. But I'm actually going to ignore like issues with limits and so on and so forth in this talk because it's not very relevant for the intuition. And now, I mean, Rényi in his work, this is from the 50s, he actually introduced the Rényi information dimension as a generalization of a measure of amount of information to general distributions. It's not just that I made that up, so that's what he also says when he motivates the work. So again, we could have here like, so if we look at the idea of that, right, you would quantize x with a uniform quantizer of step size 1 over m, you compute the entropy, and then you let m tend to infinity and you see what happens. And if he believed that this formula here makes sense, and I mean Rényi was a smart person, so probably does make sense, then he would basically get that the entropy is equal to this information dimension times log m plus some, well, let's say second order asymptotics plus some terms that go away if m tends to infinity. That's somehow the idea. Right? Good. Now there's some basic properties we know about information dimension. So first of all, it's not always finite, but we know it's finite if and only if the random variable has the integer part of the random variable has a finite entropy. And you can show that this is true, well, or a sufficient condition for this to be true is that this expected logarithm is finite. And that was finite in many cases. So if you have a finite variance, it's finite. Actually, that's satisfied for all kind of heavy-tailed distribution. Like you can look at, if I want to look at something weird, I usually look at Cauchy distributions, right? They don't even have a variance. But I mean, so that one's also finite for Cauchy. You can look at log Cauchy, whatever. But you can find distributions where this is not true. Okay, you can find actually distributions where this is not true. well, I skipped these two, but I think that one is also nice. So if you talk about boundedness, so now here, yeah, this should be the information dimension of a sequence of x from 1 up to k. Okay, that's a typo. So you can actually define information dimension also for vectors. The only thing you do is you quantize each component with a uniform quantizer. Apart from that, it's exactly the same thing. Right? And what you can show that if the information dimension is finite, then it's never larger than the dimension of your vector. Right? So that's why it's a dimension. You know.
So do you divide by log m or log m to the k?
No, you divide by log m. Yes. Another thing that is interesting, I think, is so if X has a covariance matrix, then you can show that the information dimension is never larger than the rank of the covariance matrix. It's basically, if you want, is like the essential dimensions a random vector has. And you can show that this holds with equality if X is Gaussian. It's not only in the Gaussian case. You can find a lot of other random variables that also satisfy this equality, but somehow like also Gaussians maximize not only entropy, but also like information dimension. Now there's a celebrated result in Rényi's original paper which studies the case if X has a mixture distribution of a discrete one and a continuous one. Right? So if your distribution is one fraction of it is continuous, the other one is discrete, then what Rényi showed is he showed that the information dimension is equal to the fraction of the continuous part. Okay? So the discrete part actually has 0 dimension and you only get with the continuous one. And he even computed like the second order term, which he called the d-dimensional entropy, which is given by this here. So you have basically like the entropy of the discrete random variable plus here you have the differential entropy of the continuous one, and then you have a binary entropy function of rho. So basically you have right, in a way one part of the information is the discrete part, the other one the continuous part, and then obviously another part of the information is like how much discrete and how much continuous do you have in your random variable. And now if you go to the two extreme cases, right, so if you're in the discrete case, this means that your rho is 0, right, because you only have this distribution here. So if you specialize this to this case, you get that the information dimension is 0 and the d-dimensional entropy is equal to the entropy, which I think is somewhat intuitive, because if you have a discrete random variable at one point, right, quantizing finer doesn't change anything, right? If your quantization like step size is small enough, you're already at the entropy anyway, and nothing changes by letting this tend to 0. On the other hand, in the continuous case, you get that the information dimension is 1, and the d-dimensional entropy is the differential entropy. And well, I mean, if you go back to this here, right, if this is positive, then the entropy of that one actually goes to infinity, right? So if you have a continuous random variable, the information of the random variable is actually infinite, which again, if you think about it, it's not that surprising, right? Because if you have a random variable with a PDF, you can always zoom in more and you always get some uncertainty. So there's an infinite amount of information actually. And it also turns out that this differential entropy is only the second term in the asymptotic expansion, right? So it sort of shows up, but it's not the information of your random variable, because the information is infinite, right? Yeah, so we talked about mixtures of distributions. You can actually generalize that to countably many distributions. You could basically say, well, you have a whole bunch of distributions, and then you have this random variable that decides which one you pick. And as long as this random variable has a finite entropy, then you get that the information dimension of this random variable is nothing else than the average of the information dimension. So this is a proof in a paper by Wu and Verdu. It's that long, so it's not difficult to show these kind of things actually. It's just nice. You could, from that you can recover again the discrete continuous mixed distribution. Fine. Now so far we said, right, so Shannon's approach was you quantize your random variable, you let the quantization become finer and finer, and then you see what happens to figure out what information is. And Rényi took like a uniform quantizer. And I think it's a valid question to ask, like suppose I use a different quantizer, do I get a different dimension? Right? Because potentially, like a uniform quantizer is not optimal, so you might do all kind of other things, so you could quantize it differently. So what happens if you use a different quantizer? And I guess in the extreme case, what you could do is you could say, well, instead of just quantizing each random variable separately, I could group n random variables together, and then I use the best vector quantizer I can find with a given distortion, let's say d. Right? So I want to have here, let's say, like a mean squared error that is smaller than n times d. And then, of course, we know the smallest rate that we can get is the rate distortion function. This is the best vector quantizer, at least if n is large. So we could use this quantizer, and then we let d tend to 0, and then we see what happens. And, well, at least in the Gaussian case, we know the rate distortion function is pretty much equal to 1/2 log 1 over d. So this will be more or less the behavior on how fast this goes to infinity if d goes to 0. So you can define the rate distortion dimension at this pre-log factor here. So it's basically the rate distortion function divided by minus log d, and then you let d tend to 0. Okay? So this is one way of you could define it. And well, there is work by Kawabata and Dembo who showed that for every random variable, the rate distortion dimension is actually the same than Rényi's information dimension. So at least in terms of this pre-log factor in front of the term that goes to infinity, so this doesn't depend on how you quantize it. The second order term, that will depend. I mean, that one we know from quantization theory that it makes a difference whether you use a uniform quantizer or a good vector quantizer. Okay? Right. Now, okay, so we basically did this work for fun, but there are people who care a lot about operational meaning. So, and there is work that shows that, yeah?
Just in the previous slide, you called it the rate distortion dimension, but you take the limit d to 0.
Yes. Right, so which means, again, you want a quantization to become finer and finer, right? Right, so it's... Yeah. Any other questions?
You're not allowing a distortion at the end. I mean, you're taking...
Right, because, yeah, but I mean, in a way, right, if you want to know what happens with the random variable itself, you want the distortion to go away, right? So it's otherwise, yeah, it will not be this, it's a different random variable otherwise, right?
Just to clarify, this dim R is the extension of the concept of information dimension to non-uniform quantizer.
Yes, and it's not just non-uniform quantizer, it's actually non-uniform quantizers on a sequence of n random variables. Yeah. Whereas what Rényi does, he takes the random variable itself and quantizes it, right? So it's even, right, you even do a vector even if the sequence is I.I.D, you actually look at the vector quantizer for n symbols. Yes. Well, we'll see later on what you could do if it's not I.I.D. I mean, there's a generalization of rate distortion function for the non-I.I.D case, right? So, but yeah, so you assume X is I.I.D, but it's, yeah.
How is it affected by the choice of the distortion measure?
That's a good point. It's not, yeah, not much. So basically what you need a distortion measure that is somehow like sandwiched between two norms. And as long as that somehow shrinks, you actually get the same thing. Okay, so it's pretty general actually. So I think as long as you have some convex shape for your quantizers, you're fine. Yeah.
So the limit, if the limit doesn't exist, so the choice of lim2 or lim does matter, right?
Well, of course you have to use then lim_sup or lim_inf in both cases, right? So for the rate distortion dimension and information dimension.
Okay.
Right. So yeah. So I mean, if the limits don't exist, I think they don't exist in both cases, and then yeah, as long as you choose limits, like the same kind of limits in both cases, you get the same thing. Okay. Any other questions? If there are questions, I don't have to feel bad if I go over time now. Do I have to do anyway? Okay.
I can be late, you can't.
That's unfair. Anyways, I said so. Information dimension is it's not so for us. It's something that's just interest, like on a fundamental level, but it actually shows up in some other works. For example, there's work by Wu and Verdu on almost lossless analog compression, compressed sensing. I'll talk about that in a second. It also pops up if you want to study the degrees of freedom of the Gaussian interference channel. And I mean, not so surprisingly, I guess it shows up in rate distortion theory. I mean, it's some sort of quantizations. I guess that one's the least surprising, right? That there is some connection one way or the other. Okay, so what I mean by almost lossless analog compression. So I guess, so suppose you have an encoding function f that maps an n-dimensional real-valued vector to a k-dimensional real-valued vector. So you want to describe the n-dimensional vector by a k-dimensional one. And then you have a decoder that basically reverses this operation. And then we define the minimum epsilon achievable rate as the smallest rate, k over n, for which the probability that you make a decoding error is not larger than epsilon, right? Now, if you would replace the real numbers here by bits, then this would be like the lossless compression part, right? And the rate would be the entropy of the source. But here we have like real numbers. It turns out if you have real numbers, then this problem, if you don't restrict the functions of the encoder and decoder, and this is very boring because you can take an n-dimensional real-valued vector and you can describe it with one real number, right? You can embed it in one dimension. So the rate would actually always be 0 unless you put on some restrictions on those functions. And what Wu and Verdu showed is, so suppose you have like an I.I.D. sequence which has a discrete continuous mixed distribution, right? And suppose either the encoder is linear or the decoder is Lipschitz continuous, then this minimum epsilon achievable rate is equal to the Rényi information dimension, which is equal to the fraction of the continuous part. Okay, so there is some fundamental or operational meaning to this, at least for this specific example. And I guess especially the F is linear case is interesting because this is like what you have in compressed sensing, right? You have basically a linear observation matrix from which you do things. Okay? Good. Now that was sort of the introduction about what happens at I.I.D. So together with Bernhard, we're interested in like what happens if you go to the I.I.D. if you go beyond the I.I.D. case. And I think first of all, conceptually, if you go to processes, so this is much more interested than I.I.D. sequences because they have a lot more properties and on a whole, like you have a different dimension of having dependencies. So let me first motivate why I think it's interesting to study the information of processes. And I would like to do that by means of Gaussian processes because these are the ones we understand the best, right? So we have a stationary Gaussian process with a given mean, a given variance, and then we have this spectral distribution function. So I don't know how many of you are familiar with this. It's basically generalization of the power spectral density. So you have here on the left-hand side, this is the autocovariance function, and then you can show that this is equal to this Lebesgue-Stieltjes integral of the spectral distribution function. Now this here is a distribution function, but with the difference that it tends to the variance and it doesn't tend to 1. Right, so it's not a probability distribution function, but apart from that is exactly the same properties, so it's increasing, like left continuous and so on and so forth. So we know that this is differentiable almost everywhere, and we denote its derivative by fx prime. And well, we know that if this is absolutely continuous, then the derivative is nothing else than the power spectral density. That's why I'm saying it's a generalization of this concept. Now, if you want to understand what is the information of a process, I think one way of doing that would be to understand what is the conditional distribution of a sample at time t conditioned on the infinite path. Right? At least in the stationary case, I think that's basically what you're interested in. And now, in the Gaussian case, this is nice because we know the mean is some linear combination of the past samples. And we know the variance is given by this formula here, so this is nothing else than like the one-step prediction error. Like this formula is very old, right? It's due to Kolmogorov and Wiener and so on and so forth, right? So we basically have here like the logarithm of this derivative of the spectral distribution function, okay? And I didn't write out the mean much because the information, I guess, will probably depend more on the variance that you have, right? Because the variance determines how much uncertainty you have. And now there are two cases to differentiate, right? I guess the first one is where this variance here is strictly positive. So these processes we call non-deterministic. Well, now in this case, you will probably, you will have that this sample conditioned on the past has a PDF, right? And if it has a PDF, we will probably expect that the information of this process is infinite, as we've seen in the I.I.D. case. The other case would be like the case of deterministic processes. So if the variance is 0, and I think there things are a bit more interesting because, well, on the one hand, the sample itself has a PDF because it's Gaussian. But if you condition on the infinite past, it actually doesn't have a PDF anymore because it's deterministic. So I guess it's a fair question to ask. So in this case, is the average information per sample now for this process, is it finite, is it infinite? Like what happens in this case? And now you might argue, well, yeah, but this case is surely a pathological case. Like when can you predict the process from its infinite past, right? This is, again, like sort of now here comes my engineering education again, right? That's never possible anyway, and if it's possible, it's not a relevant problem for us, right? But it actually turns out, so this is 0 whenever this integral here is minus infinity. And this is the case as long, for example, if this thing here is 0 on an interval of positive length, then this integral will always be minus infinity. So for example, if you look at processes with a band-limited power spectral density, they always have a prediction error that is, well, that tends to 0 as the path in which you observe tends to minus infinity. Okay? So it's not an entirely pathological case, actually a lot of interesting cases there. Okay? Anyway, so if you want to study the average information of this process, we can now do the same trick we did before. So we quantize the process, we compute, or we figure out what is the information of the quantized process, and then we let the quantizer to become more finite. Right? So first thing is we have to figure out what is the information of a stochastic process. But that one actually is not very difficult, I guess. So if you have a stochastic process, you can define here, like this is what we call the entropy rate, right? So you look at the entropy of a sequence of random variables, and then you divide by n, let n tend to infinity. Now this definition works also if x is not stationary ergodic, but if it's stationary ergodic, the fact that this measures the uncertainty of a process becomes clear, because you have basically like the Shannon-Macmillan-Bryman theorem that Jung-Han Kim mentioned yesterday, which says that if you have a stationary ergodic sequence, and if you look at like a long sequence of samples, let's say x1 up to xn, then almost all realizations of these sequences will have a probability that is roughly equal to 2 to the minus n times the entropy rate. And again, there are approximately 2 to the n times the entropy rate such realizations. So you need n times the entropy rate bits to describe them, which means the average uncertainty of this process is given by the entropy rate. Okay, so this is the thing we call it. Right? So that part. So the next part would be, again, so we quantize the process by basically quantizing each sample. Again, with a uniform quantizer of step size 1 over m. We then compute the entropy rate, and we let m tend to infinity. And this is what sort of leads to, so we call this quantity the information dimension rate, which is nothing else than the information dimension, but you replace the entropy by the entropy rate. Okay? I think it's like the natural thing to do. At least that's what we thought. Well, again, we have some basic properties. So for example, you can show that it's finite if and only if the integer part of one sample has finite entropy. By the way, from now on, I will basically assume that the process is stationary. It's not necessarily necessary to do that to study information dimension rates. You can also generalize this to non-stationary processes, but it's just in a stationary case things become easier, and you at least know that one of the limits always exists, right? The 1 over n, this always exists in the stationary case anyway. So for stationary processes, the information dimension rate is finite if and only if the integer part of one sample is finite, and you again have this sufficient condition for finiteness. So the nice thing is here you only care about like the entropy of one sample, not of the whole process, right? Which is I think nice. And again, about boundedness, so you can show that the information dimension rate is never larger than the information dimension by Rényi of one sample. So if you have dependence over time, you reduce potential information. And you have equality here if the process is I.I.D. And well, you could also sort of have an equivalent result of a mixture of countably many processes, where you get that the information dimension rate then is the average of the information dimension rates. I think I'm going to skip through that quickly because it's not that interesting. What we found more interesting is like if you compute the information dimension rate for Gaussian processes. Okay? And that one, so a lot of the other results don't require that much work. So if you want to get that one, you have to work a bit. So that one is not that obvious to do. So suppose you have a stationary Gaussian process with a given spectral distribution function f. So then we showed that the information dimension rate is equal to the Lebesgue measure of the set of harmonics where the derivative of the spectral distribution function is positive. Okay? So let's make a few examples to parse that a bit better, right? So, in the easiest case, of course, if you have an I.I.D. sequence, then the derivative of the spectral distribution function is constant. So in this case, it's always positive. So the Lebesgue measure of the frequencies where it's positive is equal to 1, right? Which is what we know already anyway, right? For I.I.D. processes, the two are the same. Now, in the other extreme case, we have like a quasi-static process, right, where x of t is equal to some random variable x, but it doesn't change over time, right? So if you know the first sample, you know the whole rest. And you actually know that in this case, the derivative of the spectral distribution function is 0 almost everywhere. Which means that the information dimension rate is 0, which I think is also intuitive, right? So if there is no evolution over time, then there shouldn't be any information, right? So if you know. Now in between you have the case where, let's say, power spectral density is band limited. So suppose the power spectral density has a support only from minus W to plus W. So in this case, if you evaluate this formula, you get that the information dimension rate is equal to twice the bandwidth. Which I think has a nice intuition, right? Because this is, if you want, like sampling theorem for stochastic processes, right? So if you sample at Nyquist rate, then you just need like this fraction of sample to describe the whole process. So to give you one specific example, so by the way, so for me the spectrum goes from minus 1/2 to plus 1/2. It goes from minus 1/2 to plus 1/2. So suppose your bandwidth is 1/4. So basically the spectrum is positive only on half of your frequencies. So now on the one hand we know the information dimension rate in this case is 1/2. And I think this is intuitive, right? Because if your spectrum is positive only on half of your frequencies, then you only need every second sample to describe your process. All the other samples you can write as linear combinations of those. Right. So if you now go back to the question, like, does a band-limited process have infinite information or not? So the answer is, suppose again we look at the case where W is 1/4, right? In this case we know this process has infinite information, but it actually only has half as much information as the I.I.D. process, right? If that somehow makes sense, right? I mean, you divide infinity by 2, but still, I guess this is like the kind of thing you can only study if you go through this quantization like argument and then you let the quantization become small, right? Good. Well, okay, I'm going to skip that too. So this is like an important lemma we needed to prove that, which relates the spectral distribution function of the quantized process to the unquantized one. Anyway, so now you can also go to multivariate processes, right? So now here at each time, this is not a random variable anymore, but it's a vector. Now, not much changes in this case, so the only thing is you have now a mean vector, right? And you have your spectral distribution function now is matrix valued. Because your autocovariance function is matrix valued too, because you have a cross spectrum. So you basically have here a matrix, and then here this is an integral with respect to a matrix valued distribution function. And you can actually show, so the ith and jth element of this fx is the cross spectral distribution function between these two component processes. Okay. And again, you can show that this is differentiable almost everywhere, and we also know that the derivative is Hermitian and positive semi-definite. So there's work by Cramet on this thing and so on and so forth. So this is very well understood if you deal with stochastic processes. Now what we show is that for a stationary process with a given matrix-valued spectral distribution function, the information dimension rate is never larger than this integral of the rank of the derivative of the spectral distribution function. Okay? And there are several observations of why we like that. So first of all, like for random vectors, we said that the information dimension is not larger than the rank of the covariance matrix. So this is in a way like a nice generalization to processes, you know, where now you look at the rank of the derivative of the spectral distribution function. We also see here, so this holds with equality if the process is Gaussian. So again, Gaussian processes maximize the information dimension rate. These are not the only ones that do it. So this is like a sufficient condition. Yeah. Now, you can also see that if you go back to the one-dimensional case from this, you recover the result from before, right? So if you just have a one-dimensional process, then the rank of that one is just like the frequencies wherever the derivative of the spectral distribution function is positive. And then we get back like the Lebesgue measure of that thing. And what we also see is that if the component processes are independent, then this matrix is diagonal. And then you can basically show that the rank is nothing else than the sum of those frequencies where the derivative is positive of each component process. So you get here this sum here, which shows us that what you care about is only the support of this derivative. You don't care where the zeros are. So suppose you have two processes that are independent. It doesn't matter whether their zeros are aligned or not aligned. You just care about what is the total amount of zeros that you have, or of non-zero entries of this spectral distribution. Okay. Another result that I like is the following. So suppose you have two stationary processes. They're not necessarily independent. And we assume that one of the two processes has zero information dimension rate. So then you can show that the information dimension of the process U plus V is actually equal to the information dimension of the process U. Not very difficult to show that, but it has a nice implication. And the implication is the following. So this is maybe a bit more technical. But so we know that the spectral distribution function can actually be written as the sum of three distribution functions. One of them is absolutely continuous, the other one is discrete, the other one is singular. The Lebesgue decomposition theorem, right, a well-known theorem. And this implies that you can write any stationary process as the sum of three mutually uncorrelated processes. So one of them has an absolutely continuous spectral distribution function, the other one has a discrete one, and the other one has a singular one. So now if we set U to be equal to the absolutely continuous part, and we set V to be the rest, then you can actually show that, well, the information dimension rate of this V is zero because the derivative of these distribution functions are zero almost everywhere. And we know that if they're zero almost everywhere, actually by this inequality you get that the information dimension is zero. So what we get here is we get that the information dimension rate actually only depends on the absolutely continuous part of your process, which I think is nice, and it actually might simplify the analysis of some processes, because if you have a power spectral density, then things become easier. Good. One last comment about like rate distortion dimension, right? Yossi asked that already before, right? So before we said we have a sequence of I.I.D. random variables. Now, and then it doesn't matter whether you quantize each sample with a uniform quantizer or whether you quantize a sequence of samples with the best vector quantizer. Now for processes that actually you can show the same thing. So now, because now you know if you want to quantize a sequence from a stationary ergodic process, right, then the smallest rate you need to describe those within a given distortion is actually equal to like this rate distortion function, where what you do is you look at the rate distortion function for k samples, you divide by k, let k tend to infinity. Right? I think it was Gallagher who showed that this is the smallest rate for which there is a vector quantizer of a given distortion. And what we showed was that for any stationary process, again, the rate distortion dimension is the same as the information dimension rate. So also for stationary ergodic processes, it doesn't matter how you quantize the process. Okay? Good. Now I feel like a fair, maybe not very nice question would be, like, isn't this all obvious, right? Because, okay, so Rényi actually came up with the information dimension, and now the only thing you do is you replace entropy by the entropy rate, but that's somewhat like intuitive as well. And then, yeah, you have some results, and some of them are neat, some others are not so difficult to obtain, right? But so isn't this all like kindergarten stuff, right? And I cannot answer that question, but what I can say is that there were other generalizations of information dimension to stochastic processes, and they're not the same as what we did. So there's one by Jalali and Poor who defined the information dimension of stochastic processes like this, which looks a bit cryptic, but you can actually show that for stationary processes what they do is they look at the information dimension of n samples, and then they divide by n and let n tend to infinity. And in all fairness, so they didn't just propose this generalization, but they also like showed that for a given class of processes it has some operational meaning and so on and so forth. So it's not, so their work is more than just a definition of this information dimension. we can actually show that their information dimension is lower bounded by ours. And there are cases where they're the same, but there are also cases where they're different. And I'm here because I'm a nasty person. I want to focus on the cases where they're different. So let's look at the information dimension of Gaussian processes again. So then you can show, so this is our formula, right, in this case. So if you have a given spectral distribution function, the information dimension rate is given by the Lebesgue measure of this thing here. In their case, it's the same thing, but it then take the ceiling. So what you get is that this is 1 unless this derivative is 0 almost everywhere. So only if the process is basically like constant, you get 0, otherwise you always get 1. Which also means that the two are only the same if they are either 0 or 1. So this is like in the two boring cases, right? One, you don't really have a process, and the other one is the case where it's I.I.D. And well, you also see that their information dimension is essentially independent of the spectral distribution function. Now, of course, tastes are different, and I'm not going to say which one you have to like more. I know which one I like more. And yeah, so I didn't show any proofs, but we have 2 papers on the archive. Some of the stuff I presented is brand new, so that one we still have to put on the internet at one point. And with this, I would like to wrap up. So again, what we did is we proposed actually like an information dimension rate to measure the information of general processes. And I think for Gaussian processes, it has a very nice, intuitive like solution. You can generalize it. Well, I showed the multivariate case. You can obviously, if you can do the multivariate case, you can also do the complex valued case. We have some further results that didn't show on conditional information dimension, and then you can talk about chain rules and so on and so forth. So far, we don't have an operational meaning for the information dimension rate, at least not one that is convincing. But as I said, we basically did this for fun, so the operational meaning can come later. And I think that's all I have to say. Thank you very much.
We have time for 1 or 2 short questions.
So can you just quickly explain the formula you have over here and the proof for this formula? So any intuitive ideas and
Right.
why Gaussian? I mean, what property you have used for Gaussian to derive this formula?
Right, so this depends very much on this formula for the prediction error that we have. Okay? So the approach is the following. So you start with this entropy here, right? That one. So you look at one quantization. Now you want to analyze this entropy. So what we did is we transformed this entropy into a differential entropy, which you can do by just using like a PDF that is like a step function. Okay? And then, well, this is still difficult to evaluate. So we compared this with the differential entropy of a Gaussian process. Okay? And then for the Gaussian process, we know what the differential entropy of this is. Right? I mean, that somehow depends on, let's say, where do I have dots? Right? It depends on this formula here. Okay. And now, what you is somehow need to figure out what is the spectrum of the quantized process compared to the original one. This is that's good I have this. Right, so here, and you can relate the two if the process is Gaussian. So you need basically Bousgang's theorem to relate like what happens if you quantize, like what is the cross spectrum between the original process and the quantized one. Like with Bousgang's theorem, this is very easy for the Gaussian case. In general, we wouldn't know. And then what happens is if you have like this kind of integral over there, so you have like a quantization error which is order 1 over m, and then you divide this by log m, you let m tend to infinity. And then it actually turns out, it depends, like this limit sort of depends on whether your spectrum is 0 or not. If it's 0, then the quantization error cancels with the log m. If it's positive, then the numerator is positive, the denominator goes to infinity, so that goes away. So this is, so there's been this work by Amos on like a pre-log for fading channels, and it's basically the same story. I don't know what you're familiar with that. I don't know whether that, in a nutshell. Yeah.
Okay. Just one more question.
I saw on a slide that there's a connection to universal compressed sensing. Can you say anything, just morally where the what are we?
Yes, so let's see where the. Yeah, so You mean the compressed sensing here, right? Yeah. So it's pretty much related to this one here. So basically, so you can.
Oh,
So you do compressed sensing, right? You have n vector, like an n-dimensional vector. You have a measurement matrix that maps this to a k-dimensional case. And then you can actually show that if your original distribution has a continuous discrete mixture, then the fraction k over n you need is basically this one.
okay, that's it.
So
This
this
is a very
is,
short question. So Ollie, we have time for your question.
Okay, it's a very nice formula for Gaussian processes. Have you tried to do the same thing for Levy processes? So processes which can have jumps?
no, that's a good point. No, we didn't. Or maybe we should. Yeah. So we don't have, I mean, we have a lot of experience of Gaussian processes. That's why we did it. We don't have as much with Levy processes, but I agree. It might be nice to look into that, but we haven't done that yet.
Thank Toby again.